In mathematics, a concave function is the negative of a convex function. A concave function is also synonymously called concave downwards, concave down, convex upwards, convex cap or upper convex. Definition: a real-valued function f on an interval is said to be concave if, for any x and y in the interval and for any t in 0, 1. A function is called strictly concave if, for any t in and x a per mil y. For a function f, ra, this definition merely states that for every z between x and y, the point on the graph of f is above the straight line joining the points, and a function f, x, is quasi-concave if the upper contour sets of the function are convex sets. Properties: a function f, x, is concave over a convex set if and only if the function a f, x, is a convex function over the set. A differentiable function f is concave on an interval if its derivative function f a euro squared is monotonically decreasing on that interval. A concave function has a decreasing slope. For a twice differentiable function f, if the second derivative, f a euro squared x, is positive, then the graph is convex. If f a euro squared x, is negative, then the graph is concave. Points where concavity changes are inflection points. If a convex function has a bottom, any point at the bottom is a minimal extremum. If a concave function has an apex, any point at the apex is a maximal extremum. If f, x, is twice differentiable, then f, x, is concave if and only if f a euro squared x, is non-positive. If its second derivative is negative then it is strictly concave, but the opposite is not true, as shown by f, x, equals x4. If f is concave and differentiable, then it is bounded above by its first-order Taylor approximation. A continuous function on C is concave if and only if for any x and y in C. If a function f is concave, and f, 0, a per mil 0 yen, then f is subadditive. Proof: since f is concave, let y equals 0. Examples: the functions and are concave on their domains, as are their second derivatives and are always negative. Any affine function is both concave and convex. The sine function is concave on the interval. The function, where is the determinant of a non-negative definite matrix B, is concave. Practical example: rays bending in computation of radio wave attenuation in the atmosphere. See also, concave polygon, convex function, Jensen's inequality, logarithmically concave function, quasi-concave function, notes. References: Krosiaks, J.P. Quasi-concavity. In Delaf, Stevena N. Bloom, Lawrence E. The Newer Palgrave Dictionary of Economics. Palgrave Macmillan. doi, 10.1057/9,780,230,226,203.1375. Rao, Sinaris US Engineering Optimization, Theory and Practice. John Wiley & Sons. PA 779. ISBN A0-470-18352-7. Varian, Hal. A Microeconomic Analysis. W. W. Norton and Company A.